Howdy! Chapter 12, Time-Dependent Circuits. In the last chapter, we introduced the law which should be the starting point for the analysis of any circuit. For engineers, this is undoubtedly the most important formula in the course. The integral of E dot dr around the closed path is minus the time derivative of the magnetic flux through the path. It is important to remember the convention that goes with this law that automatically satisfies Lenz's law. Take your right hand and grab the circuit so that it is on the palm side of your hand. Your fingers now point in the direction for the path integral, and your thumb points in the direction of the ds vector. We need to master the procedure for evaluating the integral of the electric field on the left side. The devices which we have studied are a battery, a resistor, a capacitor, and a coil. For a battery, we can read the value of the integral of E dot dr from the voltage marked on the battery. For a resistor, we can use Ohm's law in the form E equals rho J once we have assumed a direction for the current in the resistor. For a capacitor, we can use Gauss's law to determine E once we assume a charge, equal and opposite, on the capacitor plates. For the coil, we use the fact that the coil is made of perfectly conducting wire, and therefore the electric field is zero. For the right side, we need to realize that the magnetic field is the total magnetic field, which consists of fields made by the current in the wires of any circuit, plus any external magnetic field made by some other device. The magnetic flux due to the current in the circuit itself is proportional to that current, and the constant of proportionality is called L, the self-inductance. Remember, there is a sign ambiguity here. There may be an actual coil in the circuit creating a large inductance, or L may simply be a property of the geometry of the circuit. You can't make a circuit that has no self-inductance. We can now use Faraday's law to obtain the equation for any currents and charges in many circuits containing the basic circuit devices. Normally, the equation relates a quantity, like Q, to its derivatives. That means to solve the circuit, you need to solve a differential equation. Of course, most first-year students have not yet encountered such equations in a calculus class. You probably did learn about solving these equations in your mechanics class, but may have forgotten. The differential equations we will have to solve are about the simplest there are. You may or may not have a battery to contend with. If not, the solution for an RC or RL circuit is an exponential, and for an LC circuit, it's a cosine. If there is a battery, the solution has two parts, one of which is a constant. The procedure is not as complicated as it looks, and if you solve a number of circuit problems like those in the book or on old exams, you should have no difficulty. The mathematics becomes more complicated if the battery is replaced by a time-varying voltage supply, such as what you get when you plug something into an electrical outlet. The solution of the resulting equations may exhibit a resonance, just as was encountered in mechanics with a forced mass on a spring. Although the differential equations become more difficult, the underlying theory, Faraday's law, remains the same. As you see, in order to use Faraday's law, you have to have mastered just about everything we studied in this course. Summary. Perhaps the main reason engineering students have to take this course is for them to know how to solve time-dependent circuits. To accomplish this, there is no ambiguity about where to start. The law, which ties together everything we have learned and leads to the solution of these circuits, is Faraday's law. The integral of E dot dr around a closed path is minus the time derivative of the magnetic flux through the path. One can apply this to circuits containing batteries, resistors, capacitors, and coils, and can actually solve the resulting equations. If there is a time-varying power supply, the equations become more complicated, but can still be solved. Gig 'em!